Good morning all, I am Joyeta Moietree and yes, I am going to speak about my last chapter on thermal physics today. And in fact, this chapter is not only the most popular chapter, one of the most popular chapter in entire thermal physics, but is in fact in the entire physics. Because ever since I started studying a different subject called physics, any relatives who would come would ask me, did you study this chapter? Did you study this chapter? So finally, thanks to thermal physics that you made me a chance to understand this so important chapter. Thank you. Not really. Alright, so basically the chapter's name is Transfer of Thermal Energy. So when this term comes up, transfer of thermal energy, first of all what we will do is, this is something we did in the first video of thermal physics, that is literature in physics. So basically we analyzed the title in literature, so now we will analyze the title in physics, which is literature in physics. So let's see. Basically this title we understand what transfer of thermal energy means. But my question is, are we studying something advanced, that is more advanced of thermal physics, or are we actually still studying some basics? Well, you will understand it in a few seconds. That is, we basically, till now, since this is our last chapter, let's review a little. That is, we basically studied about the molecular structure of solids, liquids and gas. And then we studied the three different equations relating to properties. And then we studied how to calculate heat, heat of the matter. And then we also studied how to calculate heat when there is a state change. So all these things we have studied. So have you ever imagined that we are actually providing heat to a matter in one side, suppose in one corner or in one portion of the matter, but not from the all direction. But when we calculate the heat of the matter, we actually take the mass of the whole matter that is heated. So how come heat is supplied in one end or in one region, but the entire matter is actually heated up? That is basically called the process of transfer of heat. So transfer of heat, especially in certain matter, is basically because we mostly, when we calculate the heat in solids, transfer of heat is necessary in the whole solid, because when transfer of heat is done, that is when calculating heat comes. So we are basically going back and then we are studying some basics in this chapter. Alright, so when transfer of heat or thermal energy comes, three terms of course pops up in our mind, that is conduction, convection and radiation. So yes, absolutely right, we are going to study conduction, convection, radiation today. So basically I am not going to list out the differences between them, that these are the differences between conduction, convection and radiation, or this list of differences. No. I will basically explain you the three different processes, which are very easy. When you understand the processes, you yourself can explore what the differences are, right? So let's start with conduction. So basically, conduction at the beginning basically puts a condition. That is, in conduction, basically heat transferred through conduction, molecules cannot change their place. So when a matter is transferring heat through conduction, then the molecules in the matter cannot change their position. So when cannot change their position comes, the only name pops up in our mind is solid. Absolutely right. That is because in liquids and gas, the molecules, they are always moving. And that is why it is said that solids are really good conductors and liquids are very poor conductors. So I think it is better to understand why conduction is good in solids rather than just memorizing that conduction takes place only in solids. Alright, so we understand why conduction takes place in solid. So since now conduction takes place in solid, let's understand how this entire process works out. So wait a minute. So yes, so basically when heat energy is supplied to a matter, we know that the heat energy is basically transferred into internal energy of the molecules in a solid. So internal energy then again is the sum of the potential energy and the kinetic energy of the molecules. We already know about it. So when so basically we can say that when heat energy is supplied, the molecules, they actually gain the heat energy in form of their kinetic energy. So we always know that kinetic energy is related with movement. But what is then again, the solid molecules, they cannot move because they are in a fixed position. So they cannot move, but what they do is, gaining more kinetic energy, they vibrate about a fixed position. So vibrating about a fixed position, basically when basically heat is supplied, so that is a hotter region. So the molecules in the hotter region, they vibrate more, and they vibrate more. So like this, in a way of vibrating, they actually vibrate with the neighboring molecules, and like this way, through molecular vibration, they actually transfer the heat from the hotter region to the colder region, and then transfer heat along the whole solid. I actually have basically a diagram for you, not diagram but an easier way so that you can understand. But please consider my drawing because I am super bad at it. So you see, suppose this is a solid and these are the molecules in solid. So suppose if you give heat over here, then this is the hotter region and this is the colder region. This does not have heat. So these molecules are getting more kinetic energy. So getting more kinetic energy, these molecules will vibrate. So this molecule will vibrate with this way, and then vibrate with the neighboring molecules, and the neighboring molecules will again vibrate like this way, and then again vibrate with neighboring molecules. So like this, vibrating with neighboring molecules, this heat will reach over here to the molecules of the colder region, and that is how they transfer the entire heat along the solid, and this is the process that we call as conduction. Alright, now this thing we understand how conduction takes place, basically the process of conduction. But now then we meet an event, that is, solids are good conductors, basically conduction takes place in solid. But now we meet that some solids are better conductors than the others. Well, this is something I personally don't like. I'm very disappointed that thermophysics works out in this way, because let's give an example. That is, you have heard about the bird penguin. So let's not talk about the story of penguin. We all know it's a bird, but due to in search of food, it came to the sea, and then for swimming, the wings of penguin, it lost its geometry, and penguins cannot fly anymore. Whatever, we all know it. But penguins are good swimmers now. Alright, we only know this fact that penguins are good swimmers. But can we say that these penguins are better swimmers than the others? Or this group of penguins are better swimmers than the others? No, we just know penguins were a bird and they cannot fly anymore, and then they are good swimmers, and that's it. We don't really differentiate or create different groups and start a race between them. No. But if you see in a contrast world of us humans, we humans, I think, we are the races of them. We are the biggest races because we just differentiate between superiority. Some groups are superior than the others. Now you can divide the group based on gender, based on country, based on skin color, anything. But we are always creating this race. And I saw these discriminations in this chapter, that is, some solids are better than the others. So the solids I'm naming is metals. So when it comes to solid, again two terms pop in our mind, that is metals and non-metals or insulators. So obviously we have always learned that metals are good conductors of heat. It's not that non-metals cannot conduct heat. Non-metals that are solid can also conduct heat, but metals that are solid are better conductors of heat. But why? This is because we all know that metals, they have some free electrons in their structure. So these free electrons, they basically genuinely they move around the molecules of the metal. So we have just seen the structure. Suppose that is a solid and that is the molecules of metals are there, but the free electrons, they move about around the molecules. Now what happens is, when the heat is supplied in the hotter region, the molecules, they gain heat in form of kinetic energy, and blah blah blah. Basically, through molecular vibration, transfer of heat takes place in metal. But along with that, another process also takes place. That is, the free electrons at the hotter region, they also gain the heat energy in form of kinetic energy. So they are already moving, now gaining more kinetic energy, they gain more they gain more energy, so they can move more now. So what happens is, gaining more kinetic energy, they move with high speed to the colder region. And moving to the colder region, they basically collide with the molecules of the colder region, and that is how they transfer the heat to the molecules of the colder region. So that is why it is said that metals are better conductors than non-metals of heat. That is because in metals, in two ways conduction of heat takes place. One is free electron diffusion, which is the electron thingy, and another is molecular vibration. But whereas in non-metals that are solids, as I have said, can conduct heat, but they can conduct heat only with the process of molecular vibration, which is a little slow. That is why it is said that metals are better conductors of heat. So yes, is it just me or you as well who thinks that the word free is somehow related with superiority? Well, you ask how and why. It's super easy, because you see, if you come in terms of gender, males more free, have more freedom, superior. If you consider the year-long history of apartheid between the blacks and the whites, now they term as the people who are not white as colored people, which is still a big way of racism. But anyways, the history of the whites and the colored, they were whites, they had more freedom, they were more free, and they were superior. So yes, this having more freedom and being free is always related with superiority. But you will ask, why am I speaking about this when I was speaking about metals and non-metals? Well, what made metal better conductors of heat? You will now start explaining the process of free electron diffusion. I asked what? There is the answer, free electrons. Because metals have free electrons in this structure, then all this process takes place. But the word is free electron. Free electrons. Because metals have free electrons, that is why they basically get better conductors. They get better, superior. Well, you will say these are normal natural events. Maybe metals and non-metals, this is normal natural events of the world. But I think these small things are yet to be discovered in the world, that how are, even in our world of human, how is this thing so linked, that freedom, superiority, racism, discrimination, how is all these things so related? I think this is yet to be discovered. Alright, I might sound crazy, so let's not talk about it anymore. So now you will face one more step of drama, that is, even from metals, some metals are better conductors than the other metals. This is because some metals, they have more free electrons in their structure, and of course, more free electrons means they are better at conduction. But the thing is, let solids be good at conduction. From solids, let metals be good in conduction. Let some metals be good in conduction. Why are we so affected by it? Basically, this is the fact we need to know when it comes to rate of transfer of thermal energy, because we need to know which are better at conducting heat, so that we can find the rate of transfer of thermal energy. So when it comes to rate of transfer of thermal energy, we write the term as Q by T, where Q stands for heat and T stands for time. So this is basically the rate of transfer of heat. All right. So by now, I think you have already understood that there are some factors that determines the transfer of heat by conduction. Alright, so yes, one of the factor. Alright, before stating a factor, let me state you a formula. Basically, this is because this is Q by T equals to Ka del theta by L. Alright, Ka del theta by L. So K over here is called conductivity, is a term conductivity. So what is conductivity? Conductivity is basically simple. As I have said, metals are better conductors from metals. Some metals are better conductors than the others because they have some more free electrons in their structure. So these things is this thing, what is basically conductivity? It is the ability to conduct heat, right? So more, of course, that is conductivity. So that is why we can understand that K is proportional to the rate of heat transfer, because if conductivity is more, if the ability to conduct heat is more, then of course the rate of heat transfer will be more. So yes, that is a common sense, sort of. Now let's move to A. A is basically surface area. So here also I have a sort of diagram for you all. Alright. So you see, these two things, they are of the same length, they are made of the same material, so their conductivity is same, but their surface area is different. So, of course, looking at the equation, we will just state, okay, this one is better at conduction because this has greater surface area. No, we must first understand why greater surface area actually leads to being better at rate of heat transfer. So basically, if you see, if the surface area is more, we are always providing heat in the surface region, right? So if the surface area is more, it means there are more number of molecules and more number of free electrons in the surface, which means supplying heat at one surface region, more number of molecules and more number of free electrons are actually getting the thermal energy, and hence the rate of heat transfer will of course be more. And that is why if the surface area is more, that time the rate of heat transfer is also more. Alright, next comes is del theta. Again, for del theta I also have something to show you. So you see, they are made of the same material, conductivity same, surface area same, length same. Thing is, you see there are the differences between the two ends, the hot region and the colder region. So you see, here is 50 degrees Celsius and 30 degrees Celsius, and 100 degrees Celsius and 90 degrees Celsius. Differences between temperature in the two ends of the solid. So you say the rate of heat transfer, which one will have this greater? What? This one. 90 and 100, so big numbers. Rate of heat transfer so much. No, I said del theta, difference in temperature. Yes, 90 and 100, they are big figures, but that doesn't mean rate of heat transfer depends upon the difference in temperature between the two ends. So the difference in temperature between the two ends is 20 degrees Celsius over here and over here 10 degrees Celsius. So the rate of heat transfer will be more over here, despite the figures are bigger in this case. So yes, and one more thing is basically length. So we can understand looking at the equation that when length is less, rate of heat transfer is more. Well, but as why? Of course, because if the length is less, then it will take less time for the heat to transfer along the whole solid. So that is why the rate of transfer is more when the length is less. Alright, so with that we are basically done with the factors that actually determine the rate of heat transfer through conduction. So now, bro, liquids and gas, they have some desires too. Why only solids? So of course, you have now predicted that we are going to move to convection and radiation. So now you must be thinking, oh, okay, conduction takes place in solid, convection takes place in liquid, and radiation takes place in gas. No. Yes, conduction takes place in solid, but the things you predicted about convection and radiation, that is not correct. That is why I said, don't try to make a list of differences and memorize it. Understand the processes. Alright, let's move to convection. So convection basically puts a condition, that is molecules when transferring heat through convection will move and transfer heat along with them. So what happens in this case is, suppose heat is supplied, the molecules at the hotter region, they move up to the molecules of the colder region, and the molecules of the colder region move down to the molecules of the hotter region, and that is how, setting up a convection current, they transfer the heat. So now that we have understood that for convection, heat energy always has to be supplied at the bottom. So then from the bottom, this convection current will take place and then transfer heat. But my question to you all is, why will the hotter molecules rise up and the colder molecules sink down? Why? They can move anywhere. They can move around themselves. Why up? So think about it. I will be right back in no time. So yes, basically let's draw a sort of container. Suppose this is containing some water. So yes, since I have said that in convection molecules, they have to move and transfer heat along with them. So convection can take place in both liquid and gas, because molecules can move freely in both liquid and gas. Alright. So suppose let's consider it a liquid for now. So suppose heat is provided in this way. Alright. So suppose heat is provided in this way. So what happens is the molecules at the hotter region, they basically gain heat. So on gaining heat, what happens is, we have studied the temperature volume relationship before. So what happens on this is, when temperature rises up, volume also rises up, and when volume rises up, density actually decreases. And since density decreases, the molecules at the hotter region, they basically get less dense and they basically lighter. So due to getting lighter, the molecules, they basically rise up. And hence, the molecules at the colder region, their temperature is low, and hence, since their volume is that's why low, and hence their density will be very high. So what happens is, the lighter molecules at the hotter region, being lighter, they will basically rise up, and to take its place, the molecules at the colder region being denser, they will basically sink down. And don't think this is evaporation or boiling or something, that the molecules will rise up and then pass and evaporate into the atmosphere. No. It is that molecules of the hot region, they will move to the top of the liquid, and the cold molecules of the cold region, they will move to the bottom of the liquid. And like this way, a convection current will take place in the liquid. And this same process is in the gas. In this way, convection current takes place even in gas. So yes, since in convection we have understand that basically molecules, they shift their position and they transfer thermal energy. So now basically let's study the factors. So yep, in this case the factor for convection is Q by T is proportional to A and del theta. So A is basically surface area. We understand that. That is more the surface area, rate of heat transfer is more in case of convection. We understand that. But this del theta over here is different from the del theta in conduction. In conduction, del theta was the difference in temperature between the two ends of a solid. But in case of convection, the del theta is the difference between the temperature between the temperature of the body and the temperature of the surrounding. So suppose in this case, in the case of this liquid, the difference in temperature del theta is basically the difference between the temperature of the liquid and the surrounding temperature, which is also called as ambient temperature. And this is something actually featured from the Newton's law of cooling. That is, Newton's law of cooling states that the rate of change of temperature of an object depends upon the difference in temperature between the object and the ambient temperature. Ambient temperature is the surrounding temperature. So yes, we have now, we have known the factors, and in fact, you will see that in winter, any substance, basically any liquid or anything, it will actually lose its heat more. It will cool down very quickly. Why is that? That is because in winter, the difference between the temperature of the, basically suppose the liquid or the substance and the surrounding temperature is very big, and that's why the rate of heat loss is more, and that's why it cools down faster. So I basically have something for you. That is, suppose this is the body and this is temperature and time. So you will basically have just simply to notice something in this graph. Just look at this graph and let's observe something. So you see in time it is given 1, 2, 3, 4, 5, say all these are in minute. So suppose I want to measure or see the rate of heat transfer for 1 minute. So let's do it. If you see over here 1 minute, you will find this is the heat transfer. Basically this is the heat transfer in the first 1 minute. Now let's see in the second 1 minute. It is only this much. Isn't it less? This is because this is something I am showing it right, like this way, but it is easier if you understand the gradient. That is because you see the gradient of this one is of course higher than this one. Why? Because temperature by time it is the same as Q by T, rate of heat transfer. So at first the temperature difference between the body and the surrounding was more. So that is why the rate of heat transfer was more. But as the basically the it is cooling down, it is losing heat, and its own temperature is decreasing. Now the difference between its own temperature and the surrounding temperature is decreased, so the rate of heat transfer is also decreased, and that is why we can see the gradient is decreasing in this way. So yep, and in fact you can see in the earlier days, you might see in some movies or something, that people, they used to pour the tea from the cup into the plate and then they used to drink it. Why? Because if you pour hot tea from the cup into the plate, then it increases the surface area. So we know that more the surface area, more the rate of heat transfer. So that's why it cools faster. Alright, so now that we are done with convection, let's move to radiation. So yes, radiation. Radiation basically puts on a simple fact to us, that is, radiation does not need any medium to take place. Well, this does not mean that radiation can't take place when there is a medium. It can take place when there is a medium and when there is not a medium. Because a medium is just not a factor hindering heat transfer through radiation. So radiation basically does not need any medium. So medium is just not a factor, it can take place anywhere. Okay, so yes, so thermal radiation, what we term as thermal radiation, is basically a type of electromagnetic radiation, and it is called infrared radiation. Infrared, alright, infrared radiation. So basically, suppose you put a cup of tea in the vacuum, generally it would lose heat on earth through convection, because tea liquid. But in the vacuum still you will see that heat loss is occurring. Well, not through convection but through radiation, because radiation does not need a medium. So heat loss through radiation can take place even in vacuum as well, where there is no medium. So basically through radiation, objects of any temperature can lose its heat in all directions. Alright, so before we actually go more into this, because it is seeming very cool, let's just look at the formula for the factors that affect the rate of heat transfer through radiation. So it is Q by T is proportional to AE T power 4. I hope you understand my handwriting. Alright, so the first thing is A, which is the surface area. So yes, more the surface area, more the heat loss. Okay, now let's move to E. E is a term which is basically new to us. E basically means emissivity or the ability to emit infrared radiation. We will be looking into it a little later, but what is T? T over here is temperature of own, basically the body that is emitting heat, emitting infrared radiation. It is the temperature of the own body. So that is why I say that basically objects at any temperature can lose heat through radiation, because in conduction we saw difference in temperature between the two ends. In convection we saw the difference between temperature between the ambient and the body, but in this case the temperature of the own body only matters. So no matter what the temperature of the body is, heat loss through radiation can take place. And the T over here, temperature, it is always in Kelvin. So the formula is Q by T is proportional to AE T power 4. So one value actually seems a little vague to us, that is E, which is called emissivity or the ability to emit infrared radiation. Well, we understand what E means, but how is emissivity linked? Basically, what makes once E go higher or E go lower? Okay, it sounds ego. It's not ego. Basically, what makes the emissivity of an object more? Alright, so this is basically dependent on the color and the texture of the surface of the object that is losing heat. So black and dull surfaces, they are very good absorbers and good emitters of infrared radiation, whereas white surfaces and very bright surfaces, they are basically better reflectors of infrared radiation. And in fact, let me state you a fact, that is, all good emitters are good absorbers of infrared radiation, and that is why black and dull surfaces, they are both the good absorbers and good emitters of infrared radiation. So yes, since we are talking about absorbing and emitting, let's look at two small little cute graphs. As I've said, they are cute. So let's first bring in this one. So this is basically showing in case of absorption. So there are two graphs. You must say which one is a graph showing the rate of basically the absorption of infrared radiation of a black surface and a white surface. So we can clearly say that this is of course of the black surface, because it has a higher gradient, because black surfaces, they are better. They are better at emitting and absorbing as well. So of course, since this have a higher gradient, this is the black surface and this is the white surface. Alright, now let's move to emission. So now we have to say, based on emission, which one is actually the black surface and which one is actually the white surface. Of course, this one is the black surface because it has a you can look at the gradient and you can understand. So please don't try to memorize that. The top graph is the black, and in case of emission the bottom graph is the black. No, not like this way. I know graphs seem a little confusing, but what I will actually honestly try to bring a video on graph. Maybe not very soon, but I will try to bring it sometime in future. I don't know when. Alright, so yes, and now last but not the least, I will provide you a very interesting information, that is, in fact, did you know that for objects of same volume, the surface area of sphere is minimum? And in fact, that is why you will see that in winter, when dogs are lying on the street and they are sleeping, you will see that they are sort of curled and trying to sleep in a little spherical shape. That is because to reduce the surface area. Because for objects of same volume, a surface area of sphere is minimum. So when the surface area is decreasing, so we all know for radiation, when the surface area is decreasing, rate of heat loss through radiation is decreasing. So they are losing less heat. This works for in case of winter. Even in winter, you will see when we are really shivering, we are sort of curled up, and when we sleep, we also try to go into a spherical shape. That is a natural instinct to reduce the surface area of the body and then reduce the heat loss through radiation. So yes, now that we are done with understanding three processes, so popular processes, conduction, convection, and radiation. You know, understanding a popular topic makes you feel a little cool. Oh, I know this. This is awesome. Alright, since we are done, let's move into MCQ. As always, I have picked up one MCQ from the O-level paper for you all. So let's read it out. I know you will answer it before me. So yes, the tubes inside solar heating panels use sun's radiation. Let me read it again. The tubes inside solar heating panels use sun's radiation to warm water. Why are the tubes painted black? Option A, black surface absorbs radiation well. Option B, black surface conducts heat well. Option C, black surface emits heat well. Option D, black surface reflects radiation well. Okay, option C was a black surface emits radiation well. Alright, so basically what is the answer? So over here, you see two correct information given. That is option A and option C. Option A is black surface absorb radiation well, and option C of black surface emit radiation well. Both the information are correct. But which one to choose? Because this is MCQ. Both are definitely not correct. This is when you just have to use a little of your intelligence to understand the situation. Because based on the situation will be your answer. So, you see the situation is the tubes inside the solar heating panel use sun's radiation to warm water. So, when you are using sun's radiation to warm water, what do you need in this case? The process of absorption. And that is why the answer in this case is black surface absorbs radiation well. So, in this sort of case, when two correct answers are given, you have to basically understand the situation and answer it on your understanding basis. So yes, we are done with MCQ as well. So basically, as I've said that this is the last chapter of thermal physics. So according to the rule, thermal physics was supposed to be dead by today, but I will bring a review video on thermal physics. So thermal physics isn't dead yet. Ha! Alright. So yes, thermal physics isn't dead yet. One very last video will be coming very soon, but that will be very short, don't worry. And yes, after that I will move to other subjects a little. And yes, as I have said, graphs, hopefully someday. If you want, graphs will come. Alright, so thank you so much. And yes, stay home, stay safe and stay cool. Thank you.